So now we can just quickly look at some of the, we will look at the different types of the semiconductor materials. We have devices like thyristors, which are mainly used. So these are temperature sensitive, they're mainly used to determine temperature. We saw that even from our graphs that the changes between conductivity and temperature are measurable, and that relationship is something that is taken advantage of. So they take advantage of the predictable variation of conductivity with temperature in intrinsic semiconductor materials. So they are used in temperature measuring devices, sensors, and the like. We also have the pressure transducers. So the band gap of a semiconductor is dependent in part upon the spacing between atoms. So we can actually manipulate the band gap through the application, the increase of pressure. So we increase the density of this material, we compress it, and even at the atomic level, there's a reduction in that in that space, that energy gap. So the energy gap decreases and conductivity increases. So similarly, these devices, pressure transducers, can actually be used either as sensors, where they can measure pressure differences, pressure changes, or they can be used in the opposite way as switches, where pressure is the one that causes conductivity to stop. That's how most of these devices can work either way, either as actuators or switches, where in one sense, we can use them as a sensor, and then in the opposite, we can use them as a switch. So it just depends on the application. So those are the pressure transducers. Okay, so we have what we call the diodes. So these are, I can say, the basic semiconductor device. And if we look at it at the basic level, most of the other devices can be assumed to be a combination of a diode, where we have maybe a PNP, or we'll look at transistors, etc. But basically, the PN junction forms the basis for many of these semiconductor devices, which will be discussed. So when we form this PN junction, so in essence, I don't think we get a positive semiconductor and join them. In most cases, we just have one basic silicon crystal. One side you dope it with the group 3, the other side you dope with the group 5, and then there's that diffusion which occurs, and then we have a device where there is that junction which forms. So the electrons are concentrated on the N side, and then we have the holes are concentrated on the P side. So obviously now at that junction here, we have something that will be happening there. There will be that recombination. So at that zone here, we have the positive holes and the negative electrons. There will be that recombination, and that neutralization will happen. So there is that layer here just at the junction, which we call the recombination zone. So this is at the equilibrium state when we have no current, we have no voltage being applied across this device. So just at that junction, the equilibrium zone, there will be that recombination which will be happening. So there will be that slight, so right here, there will be electrons which will cross over, and they will be recombining with these holes, and there will be that, they will form some kind of barrier where no more electrons can actually cross over once there is that recombination zone or recombination layer. So as you can see even from this diagram here now, when we actually apply a voltage across, so we apply a voltage. So this is a positive voltage with respect. So positive with respect to the P side, and negative with respect to the N side. We actually, this is what we call the forward bias. So in such a situation now, we actually energize these electrons enough. So once they cross over, they are energized enough such that they're able to cross that recombination zone, and we have that flow of current that will occur. So this is when we connect in forward bias. So that is positive with respect to the P side and negative with respect to the N side. Now the converse happens when we connect in reverse bias. So when we do the opposite now, so basically, instead of the recombining happening, there will now be that depletion. So this layer will keep growing such that there will be that greater separation and to be a depleted zone. So in this region, we have these electrons here would have combined. For example, on the P side, we have these aluminum atoms from the dopant. From the E side, the N side there, we have those extra electrons from the group 5, for example, the phosphorus, which is a dopant. There we have silicon as our main material. So once we have that interaction, these electrons here will actually combine with the aluminum per se on this side, forming those. So in this region, let me just use my pen. So in this region will now be dominated by these aluminum ions. So these positively charged ions will dominate this region on the P side. So we have these rather negatively charged ions have gained an electron. So basically they're negatively charged. Let me use my standing pen and not the vanishing. So this will be dominated by negatively charged ions. So these have gained a free electron. Remember, they needed one electron to complete that bonding. So in essence, there will be negatively charged ions dominating here, and then here we have those aluminiums would have now lost their electrons, and in this region, so this phosphorus rather. So this region will now be dominated on the other side of the junction, will be dominated by these positively charged ions. So this creates this barrier, electrical barrier, which requires energy in order for these electrons to cross over this junction, this barrier, and complete that current. However, when we connect in reverse bias, we are actually promoting the growth of this depleted layer. So when we connect in reverse bias, we'll have the movement of the holes further and the electrons further from the junction, and will actually encourage the growth of this depleted layer, and there will be no flow of current. So that is the diode therefore acting like a one-way valve, allowing the flow of electricity only in one direction, that is in forward bias. Yeah, that's those drawings. Yeah, so that is the basic operation of a diode. So that's a basic PN junction, and the PN junction device, that's a diode. So that is just what I was explaining here. When we have it in forward bias, we have that the recombination zone forming. These will be these electrons will be combining with the holes here, and in fact now with the increase in voltage, we have the flow of these electrons over that junction and the completion of that circuit. There in the reverse, we have the growth of this depletion zone, creating this barrier over which these charge carriers are not able to move, and in this case, there will be no flow of current in reverse bias. So now one of the main applications of these diodes is in rectification of alternating current to direct current, where we're simply trying to to convert that alternating current. Remember, alternating current alternates basically in direction from positive to negative to positive. If we draw it graphically, we usually draw it in that sinusoidal form where we have the waveform moving from positive to negative. So with direct current moves in one direction only, either the positive or the negative. We can bias it that way, and that is the major application of these diodes. Looking at that, they act like one-way valves, allowing current to only flow in one direction. So if we don't want the opposite flow, then we can stop it through the use of these diodes. So we see in our diagram there, we have what we call a half-wave rectifier. So a half-wave rectifier is the simplest type of rectification bridge where we only use one diode, obviously. This is simple and it has few components, it's cheaper. It will have its own disadvantages, obviously, but we use one diode, and then in our circuit we have a generator here, we have the diode itself, and we have some kind of resistive load. So we have the alternating current here as the input signal. So we can see it alternates sinusoidally. It moves from positive to negative to positive. So when we apply this diode, it will only allow the current in one direction. So we can either configure it to allow only the positive. So in this case, we have the positive waveforms. So the output will only be these positive waveforms. Obviously, now this is the pulsating type of current. So usually this pulsating form of direct current cannot be used in practical applications. So some kind of capacitor or filter has to be, such filter components have to be added in order to smoothen this pulsating DC into a constant DC. So this is something that you guys can try and look at in your own time. So in reality, the half-wave rectifiers are used with a filter such as a capacitor or inductor that will smoothen these ripples and make this pulsating DC applicable in many normal uses. So we can also look at the full wave rectifier. So this type, there are actually several types, but we'll look at the most common configuration, which is shown here. So again, we have our input signal alternating current there, and we wish to convert to an output of DC. So now in this case, like I said, this is alternating current. In one instance, it will move in this direction. In the next, to move in this direction. So we have this full wave rectifier bridge. So this one is composed of 4 diodes arranged in the configuration we can see. So if we were to convert now our alternating current, for example, when it's moving in this direction, we have our input here. And then obviously, for us to move forward, we need to move through this diode. I think there's just a conductor missing here. Let me use my permanent pen here. So I'll just try and draw a connection here. So in most cases, there will be this connection here. Forgive my bad drawing. Yeah. So I will use that vanishing pen again. So if we assume we have our current coming in like this, we enter here at our input. So we move through this diode in forward bias, and then we have our conductor here, which we move through, and then we now move through this diode here, which is in forward bias, and then we can have our output. In fact, I should have, yeah. So we're able to move in that way, and then we have that something like this. And then again, when it moves the current reverses, we'll move the opposite way. And then we'll have something like this. We move here, something like this, and then we'll be able to now have that output. So the combination of the output from these two, I can call them circuits, two streams, will result in this output here, which we see. So this is the full wave rectified signal. And again, it is also pulsating, but not to the extent that we saw with the half wave rectification. And the voltage output here, as you can see, is much higher. And that is a major advantage of this type of full wave rectification. We have a higher voltage output, and therefore for high voltage applications, this would be the more suitable type of rectifier bridge to use. But however, obviously, it is more costly due to the increased number of components. So we can now look at what we call Zener diodes. So if the reverse voltage is increased enough, a breakdown voltage is reached where a very large current will actually flow. So a Zener diode is basically like an ordinary PN junction diode, but normally operated in reverse bias condition, and such that a breakdown voltage is reached eventually where large current is allowed to flow. However, the normal diodes are not usually connected in reverse bias condition and are called a Zener diode. These are specially designed and highly doped PN junction diodes. So this breakdown voltage can be controlled by choosing appropriate dopants and their concentrations. Like I said, they're usually highly doped, and they are specially designed and highly doped in order to achieve this phenomena and ensure that they work efficiently. So the basic working of these Zener diodes is that when a diode is reverse biasly connected, we saw the creation of the depletion zone. However, we get to a point of saturation such that the growth of this depletion zone is so large, and there's that creation of a strong electric field, and there will be that saturation current that results due to these minority carriers, these charge carriers that are present. A sharp breakdown of this depletion layer that will allow for a sudden current, huge current, so that has reached a saturation current to flow through these diodes, and thus there will be that eventual flow of current even when connected in this reverse bias mode. So because of this special ability, these Zener diodes are usually used to control voltage in different circuits. And once that threshold current is reached, they allow the flow of current, but anything below that, they act as switches and will not allow for the flow of current. So the voltage across a Zener diode actually remains constant, and this is determined by the doping type and concentration. So they basically act as voltage controlling devices. So depending on the allowable voltage which you would like to have, then this will determine the doping concentration for that particular diode. So we can also look at solar cells. So we all know of these solar panels. We use them to convert solar energy to electrical energy. So solar cells are basically now at that very small level. We're looking at how these devices work. So they basically convert solar energy to electrical energy, I can say. So if we shine a light on a PN junction, then they absorb photons. So this is light energy, there's still the argument whether light is a wave or whether it's a particle. So here we are assuming it's a particle. So the absorbed photons create these electron hole pairs. So once we energize this PN, this device, we create those electron hole pairs. So we can either create this, we can supply this energy through thermal energy, through the introduction of a electrical field, or like in the case of the solar cells, through solar energy. So the photons create these electron hole pairs. So we bombard this device, this material with these photons, and they energize these valence electrons, and therefore these valence electrons now are able to move to the conduction band, and therefore we are now able to convert that to electrical energy. These electrons are available for conduction. That's converting that solar energy to usable electrical energy. So the electrons are attracted to the p side, and the holes are attracted to the n side. So we have a p-n junction still more, and then the electrons will be attracted to the p side and the holes to the n side. Therefore, there will be that flow of current. So we can actually determine the energy obtained from this phenomenon, or from this light energy. So how much energy, what wavelength? So in terms of light, the energy is determined by the wavelength of that light. Shorter wavelength light, blue light, for example, has got higher energy than longer wavelength light, like red light. So the input energy we would need, so this energy which we need to move these electrons across the band gap. And so basically the band gap energy, which can be produced from the wavelength of light absorbed. So we have this equation here. We have the wavelength is equal to h, which is the Planck's constant. We have c, that's the speed of light, divided by the band gap energy. We can determine the wavelength of the light that will be absorbed in this case to produce this usable electric energy. So those are the solar cells. And then we have the light emitting diodes. I can see these work in the opposite way to solar cells. In this case, the energy, basically the electric energy, electron energy, is converted to light energy in this case. So when the holes and electrons you combine at the interface of the crystal, so it's a crystal, the energy is released, and it's released in the form of light. So now, depending on the energy gap, we are able to produce light of different wavelengths, that is light of different color. If that is in the case of light emitting diode, this is visible light. So we again use the same formula and apply the same formula in order to determine the energy gap that we need. So what will be the wavelength of the emitted light? So if the wavelength of the energy is in the visible range, then we call it a light emitting diode. We are converting it to light energy through the recombination of these holes and electrons at the interface of that crystal, and this releases light energy. And again, the higher wavelength energy has higher, the higher wavelength light has got high energy. So we have the white light having highest energy, while we go to the red light, ET series, has longer wavelength and lower energy. So depending on the wavelength of light, we can actually determine the color of these light emitting diodes, which we need to use. So this again is dependent on the band gap energy as well. These are the factors that can be played around with. So if the wavelength of their energy is in the visible range, then we can see this light, and this is a light emitting diode. Obviously, they're emitting their energy emitting diodes, which are in the infrared energy state, and usually use these for sometimes when our remote controls, where we use them as control devices, etc. However, if the light is visible, we call them light emitting diodes. So we can tailor the band gap and obtain the LEDs of different colors. So in this case, we are simply playing around with the band gap and the type of doping, and we can therefore play around with the LEDs of different colors. So here we have an example where we calculate the band gap that is required to produce red LED. So that is red light, yellow light, as well as blue light. So we have the red light with a wavelength of 0.656 micrometers. We have the yellow light with a wavelength of 0.574 micrometers. And then we have the blue light with a wavelength of 0.490 micrometers. So with these varying wavelengths, what band gap is required to produce them? So we simply use our equation. We make the band gap the subject of the formula, which is 3 times 10 to the power 8 meters per second. We have Planck's constant, and we have the given wavelength there. So we can simply calculate our band gap energy, and we can see the band gap for the blue light, 2.52 electron volts is the highest. So obviously the lower range wavelengths such as red light require lower energy, while the higher energy light such as blue requires a higher energy input because of that wider band gap with a higher energy level of 2.52 electron volts. So we also have the transistors. So here we'll actually look at the two types of transistors. We have the bipolar junction transistor. So this is the most basic type, BJT type, where we have a junction. So in this case, we looked at the diode, which was a PN junction, while the transistor, there are two types, the BJT type, that is, there are two types of sandwich, where we have the NPN or PNP. So we have that emitter, base, and collector, depending on the type itself, whether in the application we are able to choose the type, whether it's PNP or the NPN. So they are used either as amplifiers or as switches in electric circuits. So now just to describe the operation of a transistor. So if we apply a relatively small voltage to the emitter side of the transistor only, so we have, therefore, we already have voltage across the emitter side, and therefore we will have that local flow. However, we would not expect there will be flow between E and B. However, there will be no flow from E to C or even from B to C. So there will be no flow across the base due to the fact that there is no voltage on the collector, across the collector circuit there. So in this case, the emitter behaves as a diode, and a proportionally small current flows through the device locally from E to B, like I've said, and the holes move from the P-type emitter to the N-type base. We have the flow moving from E to B, while the electrons there in the negative type base there move in the opposite direction. So this is between E and B only. So we can now also consider the case where we apply a large reverse bias voltage, for example, 20 volts to the collector side. So across the collector side of the transistor only, we have no voltage across the emitter side. So EB has no voltage across it, while we have that voltage across DC on the collector side. However, obviously in this case, no current flows between EB and EC because obviously there is no voltage there, and the collector behaves as a reverse bias diode, and therefore even on the collector side, there will be no current flow from C to B. In this case, on the other side, there will be no current flow as well. So this is due to the reverse voltage which has been applied. So now we can look at the case where we have both voltages applied on both sides of the device. So what do you think would happen? Will they operate as they did when we consider them as individual hubs? What would we expect to happen? We expect current to only flow from E to B, and it ends there. And then we have current also not flowing on the other side. And then we have no current flow due to the reverse bias at the collector side. Is that what we'd expect to happen? Actually, this is not what happens. And this is exactly what makes transistors special devices. So the trick to making this type of transistor is to make the bias very thin compared to the height, and it is doped. So what happens then is that when we apply this potential difference on a small voltage across the emitter side and the larger reverse bias voltage across the collector side, due to the very thin nature of the base, the holes from the emitter, remember that we have these holes that are moving from E to B. We have holes moving from E to B. Actually, due to the fact that the base is very thin, these holes actually continue their movement across the very thin base. The base is so thin that it does not disrupt the movement of these holes. They continue their movement across the base to the collector side of the circuit. So I have the holes from the emitter crossing the junction into the base, and almost all of them are pulled by the emitter. Remember that now, due to the reverse bias of the collector, almost all the holes are pulled by the collector once they cross from the emitter circuit before they can leave through the B terminal. So before they're able to leave, they are pulled across, and almost all the current entering the base therefore leaves through the collector, thus amplifying the small emitter current in the collector. So this movement of holes, due to the larger voltage on the collector side, is highly amplified, and this amplifies the small current from the emitter side. This very small current caused majorly by the movement of the holes. Remember, this is a positive type semiconductor. Through the movement of these holes being pulled across the very thin base, the collector side, these small current actually now is amplified by the greater current on the collector side, and thus we have that amplification of that current in the collector side as these holes move from the emitter to the collector side across the very thin base. That is the basic operation of these transistors. So that is the bipolar junction transistors, the basic transistor type, the BJT type. So we have other types of transistors that are in use. We also have what we call the field effect transistors, or FET in short. So these achieve the same effect as the BJT, but in a different manner. So the source and drain are physically placed apart far enough that the voltage cannot draw a significant number of carriers across the gap. So once we have the input voltage here, which controls the conductivity across this gap here, we are able to regulate the number of these carriers that cross from the source to the drain. So a signal voltage will provide an electric field that draws the carriers towards the gate. So by increasing the signal voltage input signal, we're able to regulate the number of electrons. So these actually attracted to the gate, but because of the presence
of this insulator here between the gate and the source. These charge carriers are not capable of reaching the gate. So instead, they do not reach the gate and are drawn to the drain due to the large voltage output at the drain. So this produces a very large output current, thereby similarly amplifying the small input signal. So a small input signal induces the movement of these charge carriers from the source to the gate. So by varying this input signal, we're able to vary the number of carriers that are able to reach the drain and thus regulate the output signal and also amplify that output, similar to what we saw with the other type of transistor. So, so this marks the end of our discussion on the electrical properties of materials. Like I said, even at the beginning, these are closely related to the thermal properties of materials, especially for most of these materials, which are good conductors of electricity, will in most cases also be good conductors of thermal energy as well, due to the structure itself of these materials and how their atoms are ordered at the molecular level. So we won't cover that in much detail, but that's something we can also read in our own time. But basically, due to the orderly nature of many crystalline substances such as metals, the thermal energy which is transmitted through the vibrations of atoms in their fixed positions in the lattice structure is able to be efficiently transmitted through the material, making them good conductors, while we find that materials such that the polymers, etc., are not able to efficiently propagate this conduction through their materials due to the, in most cases, disorderly arrangement of their atoms at the molecular level. So we can look at that in our own time. However, this marks the end of today's lecture and the end of the MEC 2309 lecture series. Thank you for your time.
So that concludes the MEC 2309 virtual lecture series. We have looked at not only the classes of materials, discussed them in detail, the structure of materials first of all. Eventually we came onto the mechanical properties of materials, and finally we have concluded with the electrical properties of materials. So all these various properties act as an input in the design process, and basically as engineers, our function and duty is to apply various scientific phenomena in the application of design, and in particular the design of products, infrastructure that are a service to humankind. So thank you so much for your time, and all the best.